And a complex number is an ordered pair of two real numbers, a and b, which can be written as a plus ib, where I is root over of -1 and I square is equal to -1. And a complex variable has two parts, one real part, one imaginary part. So Z can be written as.
volume 1 and volume 2, sir.
Am I audible?
Yes, sir.
So is the screen visible?
Yes, sir.
So there are two parts, a plus ib, or if you write Z as x plus iy, there is a real part and an imaginary part. So if Z is a complex number, then it can be written as x plus iy, where x represents the real part and iy represents the imaginary part. So in real part you have only real
क्वांटम
numbers.
मैकेनिक्स ना
ये मैथमेटिकल फिजिक्स है, दो क्लास जो था मैथमेटिकल फिजिक्स का, क्वांटम मैकेनिक्स में आपने पहले पढ़ चुके हैं, ठीक है. अर्लियर द फर्स्ट टू क्लास वाज टेकन बाय प्रोफेसर पात्र, and this is those classes which are being skipped at that time. Okay, so you will have quantum mechanics and mathematical physics, quantum mechanics 1 and mathematical physics during these classes, and after that Patra sir will have his class, and you will have complete of your you will complete your syllabus. Okay.
Okay, sir.
Okay. So Z is equal to x plus iy, where x is a real number, y is a real number. X represents your real part and iy represents your complex part. In real part there is only real number x, and in imaginary part you have I and a real number y. Okay, but a plus ib is not equal to b plus ia. You can see x plus iy is not equal to i plus ix. And if in the left hand side you can see a complex number in a Argand's plane, rectangular or polar coordinates, there you can say that it is in a Cartesian coordinate system. Here it is in a Argand system, where your x comma y can be written as y axis will be in imaginary axis and x axis will be real axis. So x is equal to real of z and y is equal to imaginary of z. And similarly in polar coordinates, you have if you will extend an angle theta, then you can write x is equal to r cos theta and y is equal to r sin theta. So it is in Argand plane. So this is the representation of complex number, and you can see z can be written as x plus iy or r cos theta plus r I sin theta. So that is r cos theta plus I sin theta, and exponential function can be written in terms of trigonometric function, and cos theta plus I sin theta is equal to e to the power I theta. So z can be written as r e to the power I theta, and it is a Euler identity, e to the power I theta is equal to cos theta plus I sin theta. So here r is equal to root over of x square plus y square, and theta is equal to tan inverse y by x. So complex number can be represented both in rectangular and polar system, and complex conjugate z star. Z star you can write as x minus iy. If z is equal to x plus iy, then z star is equal to x minus iy, and z star is equal to x square plus y square, which is equal to r square. So r can be written as root over of z star. And your modulus of z is equal to root over of z star, and it is the magnitude of z. You know all these things. This is just recapitulation of the things you have already known, and it is there in your course. Similarly, complex analytic functions. So a function of a complex variable f, which is a function of z, is a prescription for assigning a unique complex number to each z. The set of values for which the function is defined is called the domain of z, and you can write fz is equal to f x plus iy, which is u plus iv, where u and v are functions of x and y. Okay. Then limit continuity derivative of complex function. You know it, limit z tends to z0, f of z is equal to f of z0 is equal to L, which can be which is evident from the figure. Similarly, limit a function fz is said to have the limit L as z approaches to z0, and this can be shown pictorially in the figure. Then derivative limit del z tends to z0, f of z0 plus del z minus f of z0 by del z is equal to f dash z, and the geometrical representation is as shown in figure 10.3. The point z approaches in many different ways, and it is shown in the screen. This is the derivative. So Cauchy-Riemann condition. Consider a function fz whose first derivative f dash exists. So you can write fz as u plus iv. So z plus del z is equal to x plus iy plus del x plus I del y. So this is x plus del x plus I y plus del y. So you can write f z plus del z is equal to u plus iv, where u is a function of x plus del x and y plus del y, so also v. So the first derivative can be written as df by dz, and from the formula we have discussed now, you can write f dash z is equal to limit del z tends to 0, f of z plus del z minus f of z divided by del z. So now x tends to 0 and del y tends to 0, del x tends to 0 and del y tends to 0, as shown in the screen, and different approaches. How this is del x, this is del y, and you can have path 1 में क्या होगा, f dash z is equal to, in path 1 f dash z is equal to limit del z tends to 0, u plus iv minus u plus iv by del x. Similarly, the result will be f dash z is equal to del u by del x plus I del v by del x, and the derivation is here. Similarly, in path 2, your del x is equal to 0 you can put, as in path 1 you have put del x is equal to 0. Similarly, you can write del x is equal to 0 for path 2, and del z will parallel to y axis. So now del z becomes I del y, and you can write it as del u by del y is equal to minus del v by del x. So this is Cauchy-Riemann condition, and you have fz for a complex variable z is said to be analytic at a point z0 if it is differentiable at that point as well as at all points in the neighborhood. So the function fz is equal to z star is not an analytic function of z, as its derivatives exists nowhere in the complex plane. To enable you to appreciate this statement, you can write df by dz is equal to limit del z tends to 0, f z plus del z minus f of z by del z, and if you have your d z star by dz, you will find it is limit del x tends to 0, del y tends to 0, del x minus I del y by del x plus I del y. So by deriving it, you can have the final expression del u by del y is equal to minus 2y, and minus del v by del y is equal to minus 2y. And this is for harmonic function, del square v by del x square plus del square v by del y square is equal to 0. Then there are different functions which can be written in a complex form. First is e to the power z, which I have told you earlier. So this can be written in a series form, and you can write 1 plus z1 plus z1 square by 2 factorial plus z1 cube by 3 factorial, so on and so forth. z2 1 plus z square 1 plus z2 plus z2 square by 2 factorial, so on and so forth. So this is the representation for your exponential function. For trigonometric function, you can write sin z is equal to z minus z square by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7 factorial. Similarly, for cos z, you can write 1 minus z square by 2 factorial plus z to the power 4 by 4 factorial minus z to the power 6 by 6 factorial. Similarly, you can have tan theta, tan z, sin z by cos z on the other functions. Then hyperbolic function, sin hyperbolic z can be written as e to the power z minus e to the power minus z by 2, and cos hyperbolic z can be written as e to the power z plus e to the power minus z by 2. Similarly, your logarithm function ln z can be written as ln modulus of z plus I theta, where theta is from minus pi to pi. Then branch cut and branch point and singularity. So suppose a function is not analytic, then it can through branch cut you can have a modified one which you can have for your mathematics. Then singularity of a function, regular singularity, removable singularity, so on and so forth. Then complex integration. So these are Jordan arc. It is a closed contour. It is a smooth closed curve. It is a large semicircle with a small semicircle. So these are different geometry. Then contour integral. Integration over C fz dz is equal to limit n tends to infinite summation j is equal to 1 to n f of j zj minus zj minus 1, and C is the path integral. Then here cross cut. So this is simply connected region, and if there is another, then it is multiply connected region. Okay. So here, if we shrink it, then it can approach to 0 without leaving behind the area. But here you can see, if you shrink it, then at this point, it is not in the R. Here also, it will be not in the R. So it is a multiply connected region. This is a simply connected region. This is a multiply connected region. For simply connected region, you have no problem. But for multiply connected region, you have to make cross cuts so that you can integrate it. So for that, you have to write like this. You have to like this in the periphery. So if you put two cross cuts here and two cross cuts here, then it will become a multiply connected region. Is it visible? Is the cursor visible? Okay. Then the Cauchy integral theorem will be integration over the contour C fz dz is equal to 0, and you can prove it by applying Green's function in the original integral. Integration fz dz is equal to integration over closed contour u dx minus v dy plus I integration over closed contour v dx plus u dy. Then Green's theorem, what I have told you, your integration over closed contour C will become u dx will minus v dy will become minus of double integral or area integral r over r del v by del x plus del u by del y dx dy. Similarly, for v dx over a closed contour, you will have integration over closed contour v dx plus u dy is equal to double integral del u by del x minus del v by del x dx dy. And from Cauchy-Riemann condition, which I have explained you earlier, del u by del x minus del v by del y is equal to del v by del y, and del u by del y is equal to minus del v by del x. So you see u x v y, u y v x. So here minus, here plus. If del u is integrated partially with respect to x, then it will be equal to del v by del y. If del u by del y is integrated, then it will be minus del v by del x. So here are the cross cuts which I have told you in the previous figure, and you will solve it in a multiply connected region. Okay. Integration fz dz is equal to integration over closed contour f dz plus summation I is equal to 1 to 4 integration over closed contour in a clockwise direction fz dx plus summation from I to I is equal to 1 to 4 integration fz to dz plus integration from I to 4 integration fz dz is equal to 0, clockwise anti-clockwise. Then Cauchy integral formula fz0 is equal to 1 by 2 pi I integration over closed contour fz dz z minus z0. And you can see it here by making a cross cut, and it is the proof. Then derivative of an analytic function, you can find nth derivative of f for a z0 is equal to n factorial by 2 pi I integration over closed contour fz dz by z minus z0 to the power n plus 1. So f dash z0 will be 1 factorial divided by 2 pi I integration over closed contour fz dz z minus z0 to the power 1 plus 1 square z minus z0 square. F double dash z0 will be your 2 factorial by 2 pi I integration over closed contour fz dz z minus z0 to the power 3 or q. Okay, so this is then sequences and series, you know these power series and other series. Then Taylor series, fz is equal to fz0 plus z minus z0 f dash z0 plus z minus z0 square f star z0 by 2 factorial plus so on and so forth f to the power n z0 by n factorial z minus z0 to the power n. Then your Lorentz series, this is very important. Your fz is equal to summation n is equal to 0 to infinite an z minus z0 to the power n plus summation n is equal to 1 to infinite bn by z minus z0 to the power n, where n is equal to 1 by 2 pi I integration over closed contour c1 is equal to fz dash tz dash z minus z0 n plus 1, where n is equal to 0, 1, 2, and bn will be 1 minus 2, 1 by 2 pi I integration over closed contour c2 fz dash by fz dash dz dash by z dash minus z0 to the power minus n plus 1, where n is equal to 1, 2, 3, so on and so forth. This is Lorentz series. So these are the worked out examples. You can go through it. Then your residue theorem. So what is a residue? If a function fz is analytic in a simply connected region, in a simply connected region is a region where if you shrink the periphery, then it will be at the center without leaving that region. So this is the concept of residue for a simply connected region. According to Cauchy integral theorem, the value of integral fz dz over closed contour C is always 0, where C is a closed contour lying wholly in R. If on the other hand, fz is analytic everywhere in R except at point z0, where it has an isolated singularity, the integration over C fz dz is not necessarily 0. If C encloses the point z0. So you can have this through a simply example. Consider a function fz is equal to z square by z minus 2. So you will recognize that fz is not defined at z is equal to 2 and is therefore not analytic. So your fz has a simple pole at z0 is equal to 2, and to evaluate the integral, integration over C fz dash dz dash around z0 is equal to 2, we may select C to be a circle representing z dash minus 2 is equal to rho e to the power I theta. So your dz dash rho e to the power I theta I d theta, and you can find integration over C fz dash dz dash is equal to integration from 0 to 2 pi 2 plus rho e to the power I theta square I rho e to the power I theta d theta by rho e to the power I theta, that is equal to 4 pi I. So you can see the residue f of z0 is equal to 1 by 2 pi I integration over C fz dash dz dash. Okay, so this is residue theorem. So how to calculate residue? If the singularity is a simple pole, your residue f of z0 is equal to limit z tends to z0, z minus z0 fz, which is equal to gz0. If singularity is a pole of order m at z0, then your residue of fz0 is equal to 1 by m minus 1 factorial d to the power m minus 1 gz by dz to the power m minus 1, where z is equal to z0. Then there is an important thing, Jordan lemma. If CR be a semicircle of radius r with center at origin, if fz is analytic in the upper half plane and fz tends to 0 uniformly, as modulus of z tends to infinite for 0 smaller equal to argument of z smaller equal to pi, then you can write integration over CR e to the power imz fz dz tends to 0 as r tends to infinite. This is Jordan lemma. Then conformal mapping. For conformal mapping, you need to first understand what is transformation. A transformation or mapping is the set of equations u is equal to u comma v is equal to v, which is a function of x comma y, and that establishes a correspondence between points in the uv and xy planes. The equations are called transformation equations. If each point of uv plane corresponds to one and only one point of the xy plane and the converse also holds, it is called a one-to-one transformation or mapping. And the corresponding sets of points in the two planes are called images of each other. And the Jacobian of the transformation will be del u comma v by del x comma y is equal to in matrix del u by del x, del u by del y, del v by del x, del v by del y. And see the figure. Suppose that a point x0, y0 of xy plane is mapped under transformation to a point u0, v0 of the uv plane as shown in the figure. And two curves C1 and C2 drawn in the xy plane intersect at the point x0, y0. So if the mapping of curves C1 and C2 in the UV plane are represented by C1 dash and C2 dash respectively, intersecting at U0, V0 such that the angle at x0, y0 between C1 and C2 is equal to the angle at U0, V0 between C1 dash and C2 dash, both in magnitude and sense, the transformation or mapping is said to be conformal at x0, y0. So this is all about complex analysis. আচ্ছা, so let us have some other important things in mathematical physics course. This is group theory. So you see, you know what is a set and how to evaluate mapping in the first class. The definition of group. And, you know, a group G is set with a binary operation, which is associative. And identity relation and inverse relation holds good for it. Then a group multiplication in order two elements also matters, and where two elements of the group commute with each other, then it is commutative or abelian group, and there are also non-abelian groups. Then your subgroup G be a group and A is a subset, then you can say it is closed under the binary operation G, and the identity must always be in the group. It includes the identity E belongs to S, and if A belongs to S, then A inverse also belongs to S, where S is a group within G and is called subgroup of G. Then geometrical illustration of S3 group as shown in the screen. Symmetries of a square you can see in the screen. Then transposition and even and odd permutations. So those which can be written as a product of an even number of transpositions are called even permutation, and those which are product of an odd number of transpositions are called odd permutations. Then there are cosets of a subgroup. It is important to know that although we have denoted the coset as AH, small a, capital H, because we choose A as the starting point in the construction, all elements in this coset are on the same footing. That is, they are equally qualified to represent the coset. So you can have left coset and right coset. Then cyclic subgroups. In a permutation like P is equal to 1, 2, 3, 4, 5, 3, 5, 1, 2, 4 in a matrix form, you can see you can get a cyclic transposition. So this forms a cyclic subgroup or permutation group. Okay. Then homomorphism. Given two groups G and G dash with binary operation O dash a mapping phi such that G tends to G dash is called homomorphism. If for any two elements A comma B belongs to G, phi A is equal to A dash and phi B is equal to B dash. Then isomorphism. If the identity E belongs to G is the only element which is mapped by homomorphism phi into the identity E dash of G, capital G dash, then the mapping phi is 1 to 1. Because if A and B are distinct elements of G and they map to the same element, A dash is equal to phi A is equal to phi B, then since phi is homomorphism, we have phi AB inverse is equal to phi A, phi B inverse, which is nothing but A dash inverse is equal to E dash. Then two elements A and B of a group G are called conjugate of each other if there is a G belongs to capital G such that B is equal to G A G inverse, and the relationship is mutual because we can also write A is equal to G inverse B, G inverse inverse. Then invariant subgroups. An invariant subgroup or a normal subgroup H of a group capital G is such that all the conjugate elements of H are within H itself. So G H G inverse is equal to H. Then you can represent it in a matrix form as shown in the screen. So your DM1 can be written as plus half root 3 by 2, root 3 by 2 minus half in a matrix form. Then 3 cross 3 matrix representation of S3 you can show here in the screen. Then some representation can be reducible and some are not reducible. They are called irreducible. You can represent it in a operator formalism, which I have shown you in quantum mechanics class. Then every representation of a finite group can be made unitary by a similarity transformation. Then active and passive transformation. When you deal with the symmetry, so all concepts of symmetry and symmetry groups of physics deals with transformation. It is important to remember the distinction between active and passive transformation. So what is an active transformation? When we think of a rigid body being rotated about an axis by a certain angle, it is an example of active transformation, as shown in the screen A, active transformation. Similarly, we can keep the body fixed, but move the coordinate system by a rotation. The coordinate of the points of the body in the old coordinate system are transformed to the coordinates of the same point in the new coordinate system, and this is passive transformation, where the rigid body remains stationary and it is the coordinate system describing it which rotates. So see here, this is x and y axis. Now you rotate x axis to x dash and y axis to y dash. So this is passive transformation. Here the point was here, x1, y1, 1 comma 0, 1 comma 0. Here it is 1 by root 2 comma 1 by root 2. So the point is moved to some other point, but the coordinates are fixed. So it is active transformation and it is passive transformation. Then orthogonal group. So space inversion or matrix with reverse the sign of each coordinate. So is can be written as -1 0 0 0 -1 0 0 0 -1, which is equal to -1, which belongs to O3. So it is all about orthogonal transformation. Then Lie groups, O3 and SO3 are more elaborate example of continuous or Lie groups, continuous groups. Then your one parameter subgroup SO3, a rotation in which not just a single point, but a whole line remain fixed is called rotation about an axis. See here, rotation about an axis. Here it was the axis and it is rotated. This thing is rotated from here to here. Then the generator of one parameter subgroups, you can see in the screen. J3 is the generator of rotation about the 3 axis. So J3 square is equal to -1. J3Q is equal to -J3. J3 to the power 4 is equal to 1. Rotation about an axis in different direction do not commute. And the infinitesimal rotation matrix differs from the identity matrix by an antisymmetric matrix. By an antisymmetric matrix. So you can see here, I think I am audible. Then bilinear product here is the commutator of two matrices. Most products encountered in physics are associative products. For example, the matrix multiplication AB multiplied by C is equal to A, BC. But the Jacobi identity shows that the product in a Lie algebra is non-associative in general. Okay. The only other place a non-associative product is encountered in elementary physics is Poisson bracket in classical mechanics, and there is a Lie algebra or phase space function. Okay. Then Minkowski space and the Lorentz group. It is very much useful in relative theory of relativity. So here you can use units such as time, and you can measure it in meters with the help of a universal constant c, the velocity of light in vacuum, which represents velocity of light in vacuum, you know, and it effectively makes c is equal to 1 in the relativity formula, and velocities become dimensionless numbers. So you can recall it Lorentz transformation in your theory of relativity classes. T dash, x dash, y dash, z dash in matrix form in a column matrix will give you the 1 by root over of 1 minus v square minus v by root over of 1 minus v square 0 0 minus v by root over 1 minus v square 1 by root over of 1 minus v square 0 0 0 0 1 0 0 0 0 1 in a matrix form multiplied by a column matrix T x y z, and it relates the same event P which is specified by T comma x comma y comma z and T dash x dash y dash z dash respectively in the two frames of reference S and S dash, which means we are using passive transformation. The two frames are such that their axes are parallel and x and x dash axes are collinear, and your S dash moves with velocity v with respect to s along x-axis, and the clocks are set to so that when the origin of the two frames coincide, t is equal to 0 is equal to t dash. So Lorentz transformation is a real 4 cross 4 matrix L which transforms x into x dash is equal to Lx, such that your minus x0 square plus x1 square plus x2 square x plus x3 square is equal to minus x dash 0 square plus x dash 1 square plus x dash square plus xq square. And any real 4 cross 4 matrix that satisfies the above equation is a Lorentz transformation. Then your Minkowski space, which I have told you, it is a 4-dimensional vector space. You know, a 3-dimensional vector space in Cartesian coordinate system, but Minkowski space is a 4-dimensional space where your x can be written as x0, x1, x2, and x3, where 1, 0, 1, 2, 3 are superscripts, and the inner product or the dot product between two vectors x and y is given by x comma y is equal to x dot y is equal to x transpose eta y, and this is 4-dimensional space and is known as Minkowski space. Okay, so it is a, so you can see here the expression for x0, and this cone is called the light cone. The time axis is the axis of the cone. The positive side of the cone, that is the half cone through which the positive half of the time axis passes, is called forward light cone, and the negative axis of the cone is backward light cone. Then Lorentz group. Let L be the set of all 4 cross 4 Lorentz transformation matrices. These form a group called the Lorentz group with matrix multiplication as the group law, and the inverse of each matrix exists because determinant of L is not equal to 0, and you know that the determinant of any Lorentz matrix can be either +1 or -1. So you can have L inverse is equal to eta L transpose eta, and if you put this L transpose eta L is equal to L eta, then taking the determinant on both sides, you can have determinant L square is equal to 1. So there are some worked out examples, and SL 2 comma C stands for special linear group of 2 cross 2 complex matrices. The only special thing about elements of SL 2 comma C is that their determinant is equal to 0, is equal to 1, is equal to 1. And the fundamental fact about this matrix is that for every A belongs to SL 2 comma C, there is a proper orthochronous Lorentz transformation LA belongs to L plus so such that L A1 L A2 is equal to L A1 A2. So although the placing of subscripts on the constant Pauli matrix is like that of a covariant vector, it is not a covariant 4 vector. So you will always use Pauli matrix with a lower index. So for Pauli matrix, you can see here Pauli matrices. So it is not there. I am Pauli matrices. These are the Pauli matrices. 1 0 0 1 0 minus 1 minus 1 0 0 I minus I 0 minus 1 0 0 1. Okay, Pauli matrices. These are very much important in quantum mechanics. So this is all about your group theory. Next is your Fourier transform, Laplace transform, which I have told you earlier. Let us have a discussion on it. Okay. So Fourier transform and your Laplace transform. So these are very much important in electronics circuits and your wave signal processing. So what is a Fourier transform? Before that, let us have a complex Fourier series. I think this is been taught in the first class, Fourier transform. Am I audible? So let us have a recap. Fx is equal to a0 summation n is equal to 1 to infinity an cos 2 pi nx by t plus bn sin 2 pi nx by t, where a0, an, bn are Fourier coefficients. So this is very much important, and a rectangular periodic wave pulse with period t, you can see the same pulse in larger t, and t may make very large. This is not periodic. So for that, this is very much important. Fx is equal to 1 by root over 2 pi integration from minus infinite to infinite gk to the power I kx dk, and gk is equal to 1 by root over 2 pi integration from minus infinite to infinite fx e to the power I kx dx. So gk is called Fourier transform of fx, and fx is called the inverse Fourier transform of gk. Are you getting it? And your Fourier integral theorem, if a function fx possesses no more than the finite number of finite discontinuities, and if the integration from minus infinite to infinite fx dx is finite, then it can be expressed in form of an integral as shown here, fx and gk. Okay. So what is the physical significance interpretation? It is very much important. The Fourier series of a periodic function tells us which frequencies or wave vector or of sinusoidal waves we should superimpose, and what the amplitude of each wave should be, so that we get the original function. Similarly, the Fourier transform of a function tells us which waves should be combined to get the original aperiodic function. The only difference is that whereas it requires discrete frequencies, that is multiple or harmonics of the frequency of the periodic function to generate a periodic function, we require a continuous range of frequencies, that is all frequencies, to generate an aperiodic function. So, the dimension of the parameters in Fourier transform is of an utmost importance. And as far as abstract mathematics is concerned, the algebraic parameters such as x, k, f, g need not have any physical meaning, and hence need not be assigned any physical dimensions. But in physics, we use mathematical models to describe physical situations. When we do that, each parameter must denote some physical quantity. And since the product kx appears as the argument of the exponential or the trigonometric function, it is clear that k must have the dimensions of the reciprocal of x. So if x stands for length, k stands for reciprocal of length, that is wave number. If x denotes energy, k must denote some quantity which is the reciprocal of energy. If x denotes time, k denotes angular frequency, and so on. So you can see the dimension of g should be those of the product of dimensions of f and x, and the dimension of f should be the same as the product of the dimension of g and k. For example, you may be dealing with the problem of vibration of a string. So in that case, fx will denote the instantaneous displacement of the string at the point x. So your x and f are both lengths, that is having dimension L, and then k would have the dimension of L inverse, and g those of L square. So these considerations in the back of your mind, you can have physically interpret the final results of mathematical calculation. And you appreciate these points better when you study application of Fourier transform. And Fourier transform of a single square wave pulse goes like this. Fourier transform of a single square pulse. And Fourier transform of electric field in a radiated wave. Electric field in a radiated wave, and its Fourier transform will be like this. Spectrum. Then Fourier sine and cosine transform, Fs is equal to root over 2 by pi integration from 0 to infinite gs sine kx dk. Gs is equal to root over 2 by pi integration from 0 to infinite Fs sine kx dx. Similarly, Fourier cosine transform, Fc is equal to root over of 2 by pi integration from 0 to infinite gc cos kx dk. Gc is equal to root over of 2 by pi integration from 0 to infinite fc cos kx dx. So there are many examples. You can go through this. This is there in your course material. Then our Laplace transform. This is also very much important. Laplace transform are widely used in various areas of physics, especially to solve differential equations. So you can see the Laplace transform Fs of a function small f t is defined as capital Fs is equal to integration from 0 to infinite e to the power minus st ft dt. And to express the fact that Fs is the Laplace transform of ft, you have to use the symbolic notation. What is that symbolic notation? Fs is equal to L ft, as shown in the screen. Similarly, you have inverse Laplace transform. Small f t is equal to L inverse capital Fs. So Laplace transform is having linearity, time shifting, frequency shifting, time scaling, time reversal, differentiation, integration, convolution, modulation, initial value theorem, all these things. So what is linearity? If ft and gt are two functions and fs is equivalent to lf and gs is equivalent to lg, their respective Laplace transform, then the linearity property of Laplace transform states that L f plus bg is equal to f plus bg. So then time shifting, L f of t minus t0 is equal to e to the power minus st0 fs. Frequency shifting, also known as fast shifting theorem, which is L small f e to the power s0 t is equal to capital F s minus s0. So time scaling, L f t is equal to 1 by modulus of a f s by a. Time reversal, L f of minus t is equal to capital F of minus s. Differentiation, L df by dt is equal to sf minus sf s minus f0. Say similarly second derivative, so on and so forth. Integration, L f dot g, when f and g both are function of t, is equal to capital Fs capital Gs. Modulation, L ft cos omega 0 t is equal to half f s minus I omega 0 plus f s plus I omega 0, and f and L ft sin omega 0 t is equal to 1 by 2 I f of s minus I omega 0 minus f of s plus I omega 0. Initial value theorem. If Fs is a strictly proper fraction, then according to the initial value theorem, limit t tends to O plus ft is equal to limit s tends to infinite sf s. Final value theorem. If final value exists, then this theorem can be written as limit t tends to infinite f of t, limit s tends to 0 sfs. Okay. Then second shifting theorem, if Fs is the Laplace transform of Ft for S tend will be greater than A, then Laplace transform of F t minus C H t minus C with C greater than 0 is e to the power minus Cs Fs. So in tabular form, you can see function, its Laplace transform, condition for existence. Okay, you can see in the screen, page number 40. Then Fourier transform can be applied in many physical situation. One is wave equation, then your diffusion equation, in hydrodynamics, then your uh, temperature distribution in an infinite metallic space, thermodynamics. And similarly, a Laplace transform can be used in many physical situations like damped oscillation. You can see here, this is the solid line, then displacement of a damped harmonic oscillator. Then it is also used in LCR circuit, Laplace transform. It is used in equation of motion in Newton's second law, md square x by dt square is equal to f of t. Then by Laplace transformation, you can have electromagnetic wave equation for a transverse wave propagating along the x-axis. Okay, so this was also very important. And vector space matrices and tensors we have decided. We have also uh, discussed all these. You can see here. Matrices, and tensors. We have also discussed this, and you can see here. I think it is visible. We have discussed all these things. If you have any doubt, you can ask. We have discussed vector spaces, linear independence, linear subspace, changes of bases, change in component with basic change, direct sum of vector space, product of operators, inner product or metric, orthonormal bases, construction of orthonormal bases, signature of metric, Hermitian inner product, Pythagoras theorems and Bessel's inequality, squash and triangle inequality, orthonormal bases in our earlier classes. Similarly, we have discussed matrices, linear equations and matrices, multiplication of matrices, the transpose of matrix, and symmetric matrix, complex conjugate and Hermitian adjoint, inverse, orthogonal and unitary matrix, functions of a matrix, elementary operations, partitioning the matrix, permutations, definitions of a determinant and its properties, inverse of a matrix, then a linear operator and matrix, two linear operators, then matrix, using matrix eigenvalue, so solution of eigenvalue equations in the form x is equal to 0, eigenvectors and eigenvalues and its physical significance we have discussed both in quantum mechanics and mathematical physics, inner product and orthonormal bases, real orthogonal and real symmetric matrices, for example, real orthogonal matrix, real symmetric matrix, moment of inertia matrix, diagonalization of real symmetric matrix, Hermitian and unitary matrix. These things we have all discussed. Then tensor, algebra, tensor of rank 1, tensor of rank 2, inner product and metric tensor, high rank tensor, special tensor like Dirac delta function and Kroneker's delta, del ij, Kroneker's delta, and your epsilon ijk, and contraction, and tensor product, vector and tensor fields. So if you have any doubt, you can ask now. And in the earlier class, we have also discussed partial equations, partial differential equations and special functions. And I think we have joined those classes. However, if you have any doubt, you can ask it now itself. So let us have the things what we have discussed earlier in partial differential equation class. So I think the screen is visible now. So in this course, we have discussed many things. So partial differential equation, and we have solved partial differential equation using method of separation of variables. And we have solved Laplace equation in Cartesian coordinates, cylindrical coordinates, spherical polar coordinates. And we have seen how to solve partial differential equations in many physical situations. Poisson's equation, heat diffusion equation, wave equation, integral equation, that is Fredholm and Volterra equation. Then we have discussed special functions by and different special techniques to solve those functions. So those includes Bessel function of first kind, its recurrence relation, generative function, Bessel function of second kind, spherical Bessel function, then Legendre polynomial, Legendre differential equation, its generative function and recurrence relations, orthogonality relation, Rodrigo formula, spherical harmonics, hypergeometric functions, Hermite differential equation, and solving Hermite, Legendre, and Bessel's using Frobenius series, Frobenius method, genetic function and recurrence relation for Hermite polynomial, orthogonal relations for Hermite polynomial, Laguerre polynomial, genetic function and recurrence relation for Laguerre polynomials, orthogonal relation for Laguerre polynomials, Storm-Liouville problem, expansion in orthogonal functions. These things we have already discussed. Okay, so if you have any doubt, you can ask, and I shall try to I shall try to solve those problems or try to clarify those doubts of you. So these things we have studied earlier. Okay. So thank you. And if you have any doubt, you can also ask in the next class. Thank you.